In this lesson, we're going to talk about the derivative as a function, and we're also going to graph derivatives. This first note says that in a previous section, we considered the derivative of function f at a fixed number a to be this formula. And so the concept is if we replace a, so if we replace this value here and here, by a variable x, then we're going to get a following definition, which is the derivative of function f given by f prime, and it's the derivative at any value x. It equals the limit as h goes to 0 of f of x plus h minus f of x all over h. This first example says the graph of a function f is given below. Use it to sketch the graph of the derivative f prime. So for part A, here's our function f. So f is a horizontal line. It's a constant value y equals 2. We want to graph f prime on the graph below. Remember, f prime represents the slope of the tangent line. So if you think about this function at any point on its graph, the slope of the tangent line is a slope of 0, and that's a constant slope for the entire curve. So since the slope of the tangent line of f is 0 at any point along the curve, for f prime we're going to graph a height of 0. And so our graph for f prime is a height of 0 at all values on the graph. Okay, next for part B, we have f, this straight line, its y-intercept is 0. The slope goes down 3 to the right 1. So our slope is going to be -3. Again, for this graph, at any point on the graph, we have the same slope of a tangent line. Because this graph has constant slope of -3, then to graph its derivative, we're going to go down to a height of -3, and we're going to draw a horizontal line. Again, these first two examples are both situations where the slope of the tangent line is a constant value no matter where you are on the graph. And that's why the graph for both of their derivatives is a constant height. These next two graphs are different. Obviously, they're not linear. If I trace this graph, it only exists from about right here at -2.5 all the way to 2.5. So what we're going to do when we draw our f prime, we're going to draw it within the same interval. Next, I want to note that if I were to draw a tangent line over here, you can see that that tangent line is negative and it's pretty steep. Then as we get here at -2, you can see the slope is still negative. It's not as negative as it was a little to the left. Same thing if we go to -1. The slope of the tangent line again is still negative, but again it's less negative. You can kind of think of it, kind of looks like almost -1, not quite. And again, as you get closer and closer to 0, the tangent lines are still negative, but eventually when you get right to x equals 0, the tangent line is horizontal, which has a slope of 0. So to take this information and translate it to a graph, again you're taking the slopes of tangent lines and then they become the heights of this graph. Okay, I wrote that out over here so you can write it down if you want it for reference. The slopes of the tangent lines of the graph of f become the heights or the y values of the graph of f prime. So back to this problem, you start off over at like -2.5, almost -3, and your tangent lines are negative, but they're really negative. And then as you move to the right, the tangent lines are still negative, but they're not as negative. And then again, at x equals 0, the slope of the tangent line equals 0. So I drew a little sketch right here representing f prime, and all the way over at -2.5, we started really far negative, and then as we get closer to 0, the graph comes up and up. It's still negative, and then finally when you get to x equals 0, we're finally at a height of 0. Let's do the same thing on the right. As we move over along the curve, we have a positive slope, and the slope of the tangent line is even more positive. So again, to the right, f prime is going to be positive, so you're going to draw the graph above the x-axis. Again, it's positive on the right side, but at first the slope is not very steep, and then all of a sudden, really quickly, the y values are going to go up, just like the slope of the tangent line gets bigger and bigger really fast. Okay, so here's our graph for f prime. Over here we have for part D. If we start all the way to the left, you can see the slopes of the tangent lines over here are practically 0. And then as we move to the right, they're positive. They're just not a super steep slope. Until we get to right here, it's kind of like a slope of +1. And then finally at 0, we have a slope of 0 again. Again, I want to emphasize from -infinity to 0, all of these slopes are positive slopes. The slope is the steepest right around -2, and then they start gradually mellowing out again back to 0. So that's what you want to keep in mind, is because all these slopes are positive, then this graph will be above the x-axis. So we start off practically at 0. We're above the x-axis. This graph peaks around -2, and then it comes back down to 0. So again, over here, all of the slopes are negative, so that means down here, all of this side is going to be below the x-axis. And the graph is the most steep, or the most negative, right about here, so that's where this f prime graph is going to be the lowest. We start off negative, and we dip down, and we have a minimum right there at 2. And we come back up, still negative, but we kind of coast over to a height of 0. So here's the graph of f prime. This example says given f equals x cubed minus x, part A says use the definition of a derivative to find f prime. So according to this definition, we have f of x plus h. So right here, we're going to plug in x plus h for both of these x's. And then we subtract f of x, and it's all over h. Right here, we have x plus h quantity cubed. So I'm going to use binomial expansion to write this out. Remember, for binomial expansion, I'm going to go x plus y quantity cubed. And then Pascal's triangle goes 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So instead of using x and y, we're going to use x and h. Okay, and here we have everything written out, and next we're going to combine like terms. Next, you can see all the terms in the numerator that are left. They each have an h in them, so we're going to factor h out, and now we can cancel these h's. And last step, we have a polynomial, so we're going to use the direct substitution property, and we're going to plug 0 in for h. So our final answer is 3x squared minus 1. Part B says to graph both functions f and f prime on the same coordinate axes. So for time's sake, I just plugged f into a calculator and you get this graph. Now, same thing, if we think about the slopes of the tangent lines right here all the way to this x value, they're all positive, and then they go to 0. All the way to the left, these are really steep slopes. So that means our function for f prime is going to start really high up and then get closer and closer and closer to 0. So again, I just want to emphasize right here is where the slope of the tangent line equals 0. So that's why I made f prime's graph hit a height of 0 at that same spot. Next, from here to here, the slopes of the tangent lines are negative. And then right here is probably where they're the most steep. So again, I'm going to put a dot right here where the slope of the tangent line is 0. The graph is going to dip down and then come back up. So from here to the right, all the slopes of the tangent lines are positive, and then they get really steep really quick. And here's our two graphs, f and f prime, on the same axes. This example says let f of x equal the square root of x. Find the derivative of f and the domain of f prime. So I have the formula written out. We have the limit as h goes to 0, f of x plus h minus f of x all over h. First, we're going to take x plus h, plug it into the function. Next, we're going to plug in over here, it's supposed to be minus f of x, so we'll plug in f of x. At this point, to evaluate this limit, we're going to multiply by the conjugate and multiply on the top and bottom. Remember, when you're simplifying limits where we're multiplying by a conjugate, you want to multiply out the conjugates, but you want to leave the non-conjugates as a product. So we FOIL out the numerator, we get square root of x plus h times itself is just going to be x plus h. When we multiply outer and inner, they're exact opposites, so they're going to cancel out. And then negative root x times positive root x makes just negative x. And like I said, in the denominator, we're just writing it as a product. This is great. In the numerator, these x's cancel. So now we have h's on top and bottom that can also cancel. At this point, we're going to take the limit of the top, the limit of the bottom. When we take the limit of the denominator, we're going to go limit of this term plus the limit of this term. And then on both of these, we can pull the square roots to the outside and take the limit of just the inside. And in the numerator, the limit as h goes to 0 of a constant is just equal to that constant. And right here, we have the limit as h goes to 0. So we're going to plug the 0 in for h, and we're just left with x underneath the radical. So the limit as h goes to 0 of x, since there's no h here to plug 0 in for, the limit of this x, you can kind of think of this x as like a constant. So the limit of a constant is just that constant. And then when we combine like terms, you get 1 over 2 square root of x. To find the domain of f prime, we have two things going on. We have a radical, and normally the domain of a square root is going to be from 0 to infinity. But because the square root is specifically in the denominator, your domain cannot include 0. So that means we're going to go 0, not inclusive, to infinity as our domain. This definition says a function f is differentiable at a if f prime of a exists. It is differentiable on an open interval from a to b, or similarly from a to infinity, negative infinity to b, or from negative infinity to positive infinity, if it is differentiable at every number in the interval. So again, we're just trying to introduce the word differentiable. And again, the word differentiable just means that you can take a derivative of the function at that value. This theorem says if f is differentiable at a, meaning you can take the derivative at that value, then we can conclude that f is continuous at that value. We have a corollary that says if f is not continuous at a, then f is not differentiable at that same value. This example says, where is the function, the absolute value of x, differentiable? So here's the graph of the absolute value of x. It has a vertex at 0, 0. On the left, it has a slope of -1, and on the right, it has a slope of +1. Right here, we call this a corner. The word corner is where the graph takes a sharp turn. And in context to this lesson, I want to look at the graph of its derivative. So remember, on the left, the slopes of the tangent lines are negative, specifically -1. And on the right side, the slopes are +1. So I left open dots right here, but go ahead and draw your graph like this. And then I wrote out f prime has a jump discontinuity at x equals 0. So you can see from the left, the graph is at a height of -1, and then we jump at 0, and we go to a height of 1. So we've just looked at this graphically. Next, I want to look at it analytically. So we're going to look at f prime at 0. So I set up the formula for the derivative of f at a equals 0. And we have f of a plus h minus f of a all over h. The absolute value of 0 is just 0. And we get to here. So this is a limit, and it has an absolute value expression in it. So that means we're going to check this limit approaching 0 from the left and the right. And according to the definition of absolute value, as we're approaching 0 from the left, the absolute value of h is going to equal -h. When we're approaching 0 from the right, the absolute value of h is going to be +h. And you can see that you're going to get -1 and +1. And then I wrote it out, since the left-hand limit does not equal the right-hand limit, the limit as h goes to 0 of the absolute value of h over h does not exist. And since this limit doesn't exist and it's equal to f prime of 0, we can say therefore f prime of 0 does not exist. And finally, we say f is differentiable on the interval from -infinity to 0, and then also from 0 to infinity. Right here I have a note. We have shown analytically that the absolute value of x is not differentiable at 0. Geometrically, the graph of f changes direction sharply or abruptly at x equals 0. So in general, if a graph has a sharp corner or cusp at a point, then the graph has no tangent line at that point, and therefore f is not differentiable there. Again, not differentiable means you can't take a derivative there. Right here I have another statement. It says another case of a function that is not differentiable occurs if the graph of the function has a vertical tangent line. So it kind of makes sense then that a graph wouldn't be differentiable if it has a vertical tangent line. Our next definition says the graph of the function f has a vertical tangent line at x equals a if f is continuous at that value a, and the limit as x goes to a of the absolute value of the slope of the tangent lines equals infinity. So this means that the tangent lines become steeper and steeper as x gets closer and closer to a. Next, I wanted to identify 3 ways for f not to be differentiable at a specific value. The first one is called a corner or a cusp. We've already seen an example of a corner with the absolute value of x graph. So next I want to show an example of a cusp. So you can see as you get closer and closer to a, the slopes of the tangent lines are going to get steeper and steeper, coming from the left and the right. For a discontinuity, one example could be a jump, and this graph is not differentiable at a because you have a discontinuity. And this last one is a vertical tangent line. You can see as you're getting closer and closer to a, the slopes of the tangent lines are supposed to get vertical. All right, so these are all 3 examples where f is not differentiable at a, meaning you cannot take a derivative of f at that value. This example says, consider the function, the cube root of x, at x equals 0. Determine whether f is defined, continuous, and differentiable there. So you guys graphed the cube root of x maybe back in Math 3 or Algebra 2, and we know that this function is defined at 0. And again, we can plug 0 in. The cube root of 0 is 0. So yes, this is defined at 0. Continuous. If you take your pencil or pen and you trace the graph, you never lift your pencil off the graph. So yes, the function is continuous at x equals 0. And that leaves us to whether or not it's differentiable at x equals 0. So before this specific problem, I probably would have guessed yes, because I'm like, well, it just looks like it kind of goes to 0 right here and then kind of increases. But if you were to graph this on your calculator and zoom in really far, you'll see that there's actually a vertical tangent line that happens right here. And again, if you go on your calculator and you zoom in and get a really small window, you'll see that the graph in fact has a vertical tangent line right at 0, so it's not differentiable there. So starting on the left, the slopes of the tangent lines are 0, and then they're positive, and as you get closer and closer to x equals 0, they get very positive. Similarly, on the right, we're starting off really positive, and then we mellow out and get closer and closer to 0. So here's our graph for f prime. This example says identify where f is not differentiable on the interval from -5 to 5 and explain why. So at -3, you can see we have and again, we can call this a corner or a cusp. I'm going to call it a cusp. Right here you have at x equals 0, you have a jump discontinuity. And finally at x equals 2, you have a vertical tangent line. So at these 3 x values, the graph is not differentiable. Okay guys, thanks for watching.